All right, so let's start a new chapter. Today you are going to learn about linear momentum, and this is from chapter 7. Okay, so linear momentum and momentum is basically the same thing. So sometimes we call it just momentum, and sometimes we call it linear momentum. And we call it linear momentum to differentiate it with the angular momentum that you are going to learn in next chapter. Okay. So what is the linear momentum or momentum? So linear momentum or momentum is just the product of mass and velocity. Okay, so here you see momentum. We use the symbol for momentum. We use the symbol small p, and small p is equal to mass times the velocity. Okay, and here because velocity is a vector quantity, and because momentum is just proportional to the velocity, so momentum is a vector quantity. Okay, so because of this relation, momentum is a vector quantity. Now let's say we have a an object whose mass is m. Okay, and let's say it is moving in this direction with a velocity v. Okay, so its momentum p will be m times v, and its direction will be the same as the direction of v. So momentum's direction will be this one, the same as v. Okay, because it's just this relation. Okay, by the way, do not confuse momentum with power. Okay, so here we use small p, and power that you learn in the last chapter. For power we used big P, I mean the uppercase P. So do not confuse small p with big P. Okay, all right. Now we learn about the basic definition of, the definition of the momentum. We learn about that it is a vector quantity. Now, what is the standard international unit? The standard international unit is this one. Okay, here kilogram is coming from mass, and meter per second is coming from velocity. So altogether it is kilogram times meter per second, and it does not have any special unit. So we write basically the kilogram meter per second for the linear momentum. Okay, all right. Now let's move on. Now momentum somehow is related to the force. Okay, by the way, so the force, the definition of force, I mean mathematical definition of force is this one, right? It's basically the Newton's second law. The net force is equal to the mass times the acceleration. Okay, again here you see it is the mass times acceleration. Here it is mass times the velocity. Okay, do not again confuse momentum with force. Okay, all right. Now this force is somehow connected, I mean this force is somehow related to the momentum. Okay, so how they are related? The force is related to the momentum by this equation, delta p delta t. Okay, delta p and over delta t. This is the rate of change of momentum. Okay, so delta p is the the change of momentum, and delta t is the change of time. Okay, so this is actually Newton's original second law, although we call this as Newton's second law, but Newton's original second law was this one. Okay, but how they are connected, how they are the same, I mean because this is the Newton's second law, this is the Newton's second law, they should be the same, right? So you can show that they are the same. You can start from this and you can mathematically show that this equation is exactly equal to this equation if we use this definition. Okay, so let's see whether they are equal or not. So let's start from Newton's original second law. The force is equal to delta p over delta t. Okay, now here you see that the p, the momentum, linear momentum. Yeah, so here this is a mistake. So this will be v. okay, mv, right? So linear momentum is m times the velocity, so mv, okay. Now m is constant, so you can take it out of the change, okay. So delta, you remember, delta means the change of some quantity, okay. So delta means change, because mass is a constant for an object. Mass is a constant quantity, so mass does not change. So you can take it out of the delta symbol. So what we have here is delta v delta t, and you remember that from chapter 2, delta v delta is the acceleration. The rate of change of the velocity is the acceleration. So what you see is mass times the acceleration. So you see that although we started from the original Newton's second law, that is force is equal to the rate of change of the momentum, at the end what you see is this equation, force is equal to the mass times acceleration, okay. So although uh, the the representation is little bit different, but they means the same thing. They mean the same thing, okay. All right. The next thing we are going to learn is the conservation of momentum. Okay, so in last chapter you learn about conservation of energy and conservation of mechanical energy. So here we are going to learn about the conservation of momentum, okay. So what is the conservation of momentum? So if you remember from the last chapter, conservation means constant, okay. So momentum is constant. So when momentum is constant, in any collision momentum is constant, okay. So for example, let's we have object A and object B, and let's say object A's mass is ma and object B's mass is mb, and let's say object A is moving in this direction with this velocity, and object B is moving in this direction with this velocity, okay. So once you know the mass, once you know the velocity of individual particle, you can determine what is the momentum of this particle, right? So if you know the mass, if you know the velocity of object A and object B, you can individually determine the momentum of object A and object B, right? And then they collide, okay? And after collision, let's say it is moving, A is moving in this direction with velocity v prime A, and B is moving in this direction with velocity v prime B, okay. Again, you can determine the momentum of object A and B after collision, okay. And conservation of momentum tells us that total momentum before the collision is equal to the total momentum after the collision, okay. So here you see that this is the total momentum before the collision, P1 and P2 for object A and object B, and this prime means the after collision. So momentum of object A and object B after collision, okay. So if I explicitly want to write down in terms of the m and v, it will be something like this. So here you see that the total momentum before the collision, and here you see that the total momentum after the collision, okay. So total momentum before and after will be the same, okay. All right. Now let's see whether it's same or not in a simulation, okay. I think this one, okay. So here is a simulation, and here this simulation, and by using this simulation we can show that um, that the momentum, the total momentum is constant before and after the collision, okay. So there is individual there is change in the individual momentum, but the total momentum is constant, okay. So let's say we have a red box and a blue box, okay. So red box's mass is this one. So here this is the red box's mass, 5 kilogram, blue box's mass is 3 kilogram, Okay, the initial velocity of this is 10 meter per second, and the red blue box's initial velocity is minus 8 meter per second. So that means blue will go in this direction and red will go in this direction, because red has positive velocity, blue has negative velocity. Okay, now if you multiply this, 5 times 10 is 50. So the initial momentum for red one is 50 kilogram, and the same thing here, 8 3 minus 24. Okay, so you see the initial momentum for the blue is minus 24 kilogram meter per second. So 50 minus 24, the total momentum is 26 kilogram meter per second. Okay, so conservation of momentum tells us that after the collision, the total momentum should be 26 kilogram meter per second. Okay, so let's see whether it is the case or not. Okay, so let me click on the run and see what happened. Okay, so you see that after collision, the blue is going to the right. Okay, and red is to the left. Okay, now here you see okay, so here you see that it's already, the simulation already gives us the momentums after collision. Okay, so after collision, the momentum of the red is minus 10.75, and the momentum of the blue one after collision is 36. Okay, so this is plus 36. So if you add them together, you see that it is exactly 26 kilogram meter per second. Okay, so you see that even there is a change in the individual momentum. Okay, the final moment, the total momentum before and after collision are the same. Okay, in both cases it is 26 kilogram meter per second. Okay, so in any collision, okay, if there is no net force applying to the outside, okay, or in other words, for an isolated system, I mean, if we think that these two are isolated from other, okay, then the momentum is conserved in any collision. Okay, so we'll be doing many problem using using this law. Okay, the law of conservation of momentum. All right, so now let's go back to the slide. Okay, okay, so here you see that the definition of the momentum, the conservation of momentum tells us that the total momentum of an isolated system of object remains constant. Okay, so here, for example, in this example, in this picture, these A and B are isolated from others. Okay, all right, so in any collision, the momentum is conserved. Okay, all right, so we will solve some problem using this law. Now let's move on and see what we have next. Okay, the next thing we have is the impulse. Okay, so what is the impulse? To understand impulse, let me start with Newton's original second law. Okay, so original second law tells us that the net force is equal to rate of change of momentum, delta P over delta T. Okay, so for simplicity, let me just use this force is equal to, okay, delta P delta T. Okay, now if I multiply both sides with the delta T, I get something like this. Okay, so this expression is called the impulse, and for impulse we use the symbol J. Okay, J for the impulse. and it is a vector quantity because you see that delta p, it is equivalent to delta p, that means a change of momentum, because it is change of momentum, and momentum is a vector quantity. Impulse is also a vector quantity. Okay, so impulse is equal to the change of the momentum or the force times the delta t. Okay, so the impulse is useful quantity when we have a large force acting on an object for a short amount of time. Okay, so here you see, if a large force is acting on a short amount of time, okay, or a small force acting a large amount of time, okay, in both cases you see that it is equal to the change in momentum. Okay, so when we have large force for a small amount of time, or a small force for a large amount of time acting on an object, impulse is a useful quantity. Okay, so by measuring the impulse, we can measure the change in the momentum, or by measuring the change in momentum, we can determine the impulse. Okay, all right, so we will be doing some problem based on these. Okay, so impulse is a vector quantity, and what is the standard international unit for impulse? It's basically the same as momentum, because this impulse is equal to the change in momentum. So one unit we use is the same unit as in momentum, and another unit is Newton second. So Newton second is basically comes from this expression, force for the Newton for the force, and second for the time. Okay, so both units are correct, and both are used when we solve some impulse related problem. Okay, all right, now little more about the conservation of momentum. Okay, so in the last slide we already see that momentum is conserved in any collision. Okay, but there are different kind of collision. So there are some collision called elastic collision. Okay, and there are some collision we call inelastic collision. Okay, so elastic collision and inelastic collision. So what is elastic and what is inelastic collision? So in inelastic collision, momentum is only conserved. Okay, so the only thing conserved in inelastic collision is momentum. But in elastic collision, momentum as well as kinetic energy is conserved. Okay, so when you solve a problem of elastic collision, you will have two equations. One is the conservation of momentum, another is conservation of kinetic energy. Okay, so so for example, in elastic collision, we have only equation we use is this one, m1 v1 plus m2 v2, or ma va mb vv equal to ma va prime plus mb vb prime. Okay, so this is the only equation we use for inelastic collision. Okay, for elastic collision, beside this, we have also another equation, that is the conservation of kinetic energy. Okay, so here we have two equations. One is this. Okay, and another is, second equation is half ma va square half mb vb square is equal to half ma v prime a square plus half mb v prime b square. Okay, so this is the conservation of kinetic energy. So for elastic collision, we have two conditions. One is the conservation of momentum, another is conservation of kinetic energy. For inelastic collision, we have only one condition, and that is the conservation of momentum. Okay, so what are basically the conservation of what are the elastic collision and what are the inelastic collisions. Okay, so to understand this, let's go to next slide. Okay, in our everyday life, most of the collisions are inelastic collision. Okay, in our everyday life, elastic collisions are rare. Okay, elastic collisions are rare. Okay, most of the collisions are inelastic collision. So that's good, because then we have only one equation to consider. Okay, that is the conservation of momentum. But in the atomic level, okay, if you go to the microscopic level, okay, so if you want to know what is the collision between two atoms, or what is the collision between two molecule, or two electron, for example, or two electron, I mean one electron and one proton, for example. So in that case, the I mean, we can have both elastic and inelastic collision. Okay, but for everyday life, most of the time our collisions are inelastic collision. So when the collisions are inelastic, then only one equation we have to use to solve a problem. Okay, that is the conservation of momentum. So if a collision is elastic collision, then we have two equations. One is the conservation of kinetic energy, and another is the conservation of momentum. Okay, so even the kinetic energy is not conserved in our everyday life collision. Okay, the total energy is conserved. Okay, so energy is always conserved, as we already learned in last chapter number 6. Okay, energy is conserved, but here we are talking about the kinetic energy. So don't confuse with the conservation of kinetic energy with the conservation of energy. Energy is always conserved. Okay, when we talk about the collision, we basically interested on whether the kinetic energy is conserved or not. Okay, all right, so in elastic collision, kinetic energy as well as momentum are conserved. In inelastic collision, only momentum is conserved. Okay. All right. And another thing I want to tell you is there are some kind of collision, some kind of inelastic collision. Okay, so some kind of inelastic collision where after collision, the the object A and object B stick together. Okay, so for example, we have object A and object B. Let's say object A is going in this direction, object B is going in this direction, collide, and after collision, they both move together. Okay, either in this direction or in this direction. Okay, so let's say they're moving in this direction, but together, they stick together. So if in inelastic collision, the objects stick together after the collision, we call them perfectly inelastic collision or completely inelastic collision. Okay, so remember that when we if in any problem, if you see that the collision is perfectly inelastic or completely inelastic, that means after collision the objects stick together and travel together. Okay, all right. Now before I go to the next one, let me go back to the last slide. So here you see one important difference in this picture. Okay, so here we have object A, we have object B. Object A is moving in this direction and object B is moving in this direction. So the length of A and length of B, you see they are the same. I mean the length of the velocity of A and velocity of B. So that means this length. I'm talking about this length. Okay, that means the velocity are at the same order. Okay, so they collide. Now if the collision is elastic, okay, so if the collisions are elastic, you will see that they are almost same, the length is same. Okay, we'll do at least actually I'm going to show you a simulation that will probably help you. So what I want to tell you is here you see that the in elastic collision the velocity, I mean object did not lose velocity. Okay, but here you see that the length is much smaller than initial velocity. So in inelastic collision, or the collision that we see normally in our everyday life, is inelastic collision. And in inelastic collision, the velocity, you see they lose velocity. Okay, and that's why the kinetic energy is not conserved in inelastic collision. Okay, so I'm going to show a simulation that probably help you to understand more. Okay, and the simulation is the same simulation. No, not this one. This one. All right. So for simplicity, let me. Okay, so elasticity should be 1 for elastic. Okay. Now let me make both block as the same mass. Okay. So you see that block red has mass 5, block blue has also mass 5. Okay, now block red has velocity 10 to the right, and the block blue has velocity -8. That means to the left. Okay, so again you see that the initial momentum is 50 for red, initial momentum for blue is -40. Okay, so the total momentum before the collision is just 10. 50 minus 10, that is equal to 10. Okay, 10 kilogram meter per second. And also here the kinetic energy for the red is 250, the kinetic energy for the blue is 160. Okay, so 250 plus 160, that is equal to 410 joule. Okay, so we'll see for elastic collision, this quantity, the momentum and the kinetic energy will be the same after the collision. Okay, so let's run it and see that. Okay, so few things I want to show you. The first thing I want to show you is the conservation of momentum, and then the conservation of kinetic energy, and then another thing. So first, let's see whether the conservation of momentum and conservation of kinetic energy valid or not here. Okay, so you see that after collision, so let me use another colors. After collision, the momentum for the red is -40, and the momentum for the blue is +50. Okay, so the total momentum is again +10. So +10 kilogram meter per second. So you see that tells us that momentum is conserved. So these and these are the same. How about the kinetic energy? Now you see that the kinetic energy for this one is 160 and this one is 250. So 160 joule, 250 joule, and it is again 410 joule. So again it is conserved. Okay, so we see that for elastic collision, both kinetic energy and the momentum are conserved. Okay, but if it is not elastic, if it is inelastic, then just the momentum is conserved. Okay, so here in this simulation you can control elasticity by using this line, this thing. Okay, so if I mean if it is not 1, that means it is not elastic. If it is 1, it is elastic. So for inelastic collision it is less than 1. For elastic collision it is equal to 1. Okay, all right, so once we understand this, the next thing I want to show you is this thing, the velocity. Okay, so let me erase this. So the another thing I want to show you is this one. So the red one's velocity was 10 plus 10 before the collision, and this was minus 8 before the collision. And here you see the exchange. So here you see now the red one's velocity is minus 8. So you see that this is exchanged and this is exchanged. Okay, so after collision their velocity exchanged. Okay, red get the velocity of blue, blue get the velocity of red. Okay, so this can only happen when mass of these two boxes are the same. Okay, so if masses are the same, ma and mb are the same, okay, and if the collision is elastic collision, okay, then va prime, that means after the collision the velocity of a will be equal to the initial velocity of b, and the velocity of b after the collision will be equal to the initial velocity of a. Okay, so that this simulation tells you. Okay, now you can prove this by using mathematics, by using some algebra. Okay, so by using algebra you can show that, but I'm not going to derive all the uh, uh, I mean all these. Okay, so here this is a elastic collision in one dimension. I mean it's exactly the same thing what you see in the simulation. Okay, so in the simulation you see that the object was going, one object was going in this direction, one object was going in this direction. Okay, so after collision we see that the velocity exchanged. Okay, here is exactly the same thing. In this case velocity, in this case one object is going in and both objects are going in the same direction. Okay, and even though because the collision is elastic and we assume that masses are the same, okay, the same mass, okay, the similar I mean similar to the simulation what we see in the simulation, you can show that the velocity of b after collision is equal to the velocity of a before the collision, and velocity of a after the collision is equal to the velocity of b before the collision. Okay, so here I already show it. Okay, if you are interested please go through the algebra. Okay, and if you have question let me know, but the thing needs to understand is these two things. Okay, these two final thing, and it happens on only when if the collision is elastic in one dimension and if the mass of ma is equal to mb. Okay, so we'll be doing some problem where the elastic collision is in one dimension and the mass of the objects are same. Okay, if the mass are not the same it's a little bit complicated, and here I'm not going to introduce it. Okay, now if you ask me to show because in the simulation you see that the objects are moving in the opposite direction. If you want to check that, you can go to the simulation and check the same thing. And let me show, actually see whether we see the similar thing or not. Okay, all right, so again this one so let me make it 5. So I mean if their mass are not the same then you cannot see that. Make it, let me make it 1. Okay, and we need the direction in the, so now you see that this is 10, this is 10, this is 5. Okay, so what we expect is this will be 5 after collision and this will be 10, right? Let's see. Okay, so now you see that this is 5, and this is 10. Okay, so you see that again it is valid. Okay, another thing I want to show is what happen if one box is at rest. Okay, so let's say the blue box is at rest. Okay, so that means the velocity of blue is 0. Okay, so what you expect here is this becomes 0 after collision, right? This will be 0 after collision, and this will be 10 after collision. Okay, let's see whether we see this or not. Now you see that this is 0 and this is 10. Okay, so that I wanted to show. You can do the same thing by using the algebra. Okay, but I'm not going to discuss the algebra here because here this simulation clearly show you the same thing. Okay, all right. Now the next thing we are going to learn is the center of mass. Okay, so what is the center of mass? So we normally use the symbol Cm to represent center of mass. Okay, so the center of mass of an object is a point on the object where the entire mass of the system is thought to be concentrated. Okay, so for example, let's look at these pictures. Okay, so if the materials in an object are uniformly distributed, then the geometrical center is the center of mass. For example, for this cylinder, okay, so this is the geometrical center. So if the material in this cylinder are uniformly distributed, then this center is the center of mass. Okay, for this cylinder. For this triangle, I mean, it's basically a triangular plate. So for this triangular plate, this is the center, and this center is the center of mass. For this circle, the center of the circle is the center, I mean the center of mass, and so on. Okay, so if we have a single particle, okay, I mean single object, and if the materials are uniformly distributed throughout the object, then the geometrical center is the center of mass. But what happens if a system is not uniformly distributed? I mean, the materials are not uniformly distributed in one system. Or if, let's say, if the system contains two objects, okay, and they are not uniformly distributed. So what happened? Okay, so yeah. So to understand this, let's go to the next slide, and before I discuss about the math, let's look at this simulation. Okay, let's say we have two objects. Okay, so here I have 1, 2, and 3. Okay, so the blue, red, and green are basically the object. Let me first talk about when we have only two objects. Okay, so red and blue basically the object. Okay, so if we have some non-uniformly distributed object, so here we have two particles, so one is this one and another is this one. So if we have something like this, this is the center of mass. Okay, now it's easy when the mass of red and mass of blue are the same. So for example, here you see that um, their mass are the same. So when their mass are the same, then it is basically in between these two. Okay, at the middle of these two, the center of mass will be at the middle of these two objects. Okay, but when the masses are not equal, okay, then it is a problematic. Okay, so for example, let's see if I change the mass of object ball 1. Okay, so you see that I'm making the object, the red object big. Okay, so when the red object is bigger than the blue object, you see that the center of mass is close to the bigger object. Okay, so how to know that? Okay, so there is some mathematical relation. Okay, that we can use to understand these. Okay, so that I'm going to show you in the next slide, okay, in the study guide. But let's see what happens if we have more than two particles. So now let's introduce another particle. So you see that now it's even complicated. Okay, so when there are two objects in one line, then it is the center of mass is basically in between the two objects. Okay, but when we have more than two particles, then it is even more complicated. Okay, so the mathematics we need to understand this is this. Okay, so let me go back to here, and these are the mathematics. Okay, so if we have two objects, okay, so if we have two objects, so here we have MA and MB. Okay, and you see that MA is XA from the origin. Okay, and MB is XB from the origin. Okay, so if we have something like this, then the center of mass of that object can be determined by using this equation. Okay, so this is the equation: XCM equal to XA MA plus XB MB divided by MA plus MB. So here is this equation. Okay, now when we have a system something like this, okay, we need a reference line. Okay, so you cannot arbitrarily determine XA. We cannot measure XA from an arbitrary point, right? So when we have a problem something like this, we need a reference line, and from that reference line we have to measure XA and XB. Okay, and XCM will be basically measured from that reference line. Okay, so if I give you a problem something like this, make sure you measure, let's say this is one object, this is another object. Make sure you measure both object from the same point. Okay, the distance from the same point. If you change the distance, then if you change the distance for one object, make sure you change the reference for other object too. Okay, so if not, then there will be a problem. Okay, so when you have this equation, the important thing to remember is XA and XB and XCM are all measured from the same line. Okay, same reference line, same reference point. Okay, so if you change the reference point for one object, make sure you do it for all other. Okay, so it is for two objects. Okay, so if you use this equation, you can show that where the center of mass would be. Okay, now this equation is only for two particles. If there are more than two particles, then this is the equation. Okay, so for example, let's say we have another object here. Okay, and let me call it MC. Okay, then the distance for the MC will be this distance. Okay, so this is XC, so XC times MC will be here. Let's say we have another object, MD. Okay, now this will be MD, XD. Okay, so you see that always we have to use same line. So here, this is the reference line to measure the distances. All right, so in general, this is the relation for determining the center of mass. Okay. Now, what happens if we have something like the simulation. Okay, so in the simulation you see that we have three objects, and they are not all in one line. Okay, so if we have some situation something like this, then we have to determine the x coordinate or x coordinate of the center of mass and y coordinate of the center of mass separately. Okay, so for example, if we have something like this, okay, so this is our reference. Okay, so this is our this is our origin, right? Normally this is our the coordinate origin of the coordinate system. Okay, now if we have something like this, we have to first calculate xcm and then ycm. So xcm will be m1 m2 plus m3, and then it will be x1 m1 plus x2 m2 plus x3 m3. Okay, now what is x1? So this is x1. Okay, and this is x2 and this is x3. Okay, I mean, so this is our reference line for x. Okay, so because the m3 is this one, so this is basically x3. Okay, so plugging this value here, you can find the x coordinate of the center of mass. And what about the ycm? Ycm is exactly same, but now instead of x coordinate we have to use y coordinate. So it will be y1 m1 y2 m2 plus y3 m3. Okay, now y1 is 0 because this is 0 line, right? So y1 is 0, y2 is also 0, but y3 is this line, this distance. Okay, because this is the 0 line for y, and from this one this is 4. Okay, so there will be only contribution. So this will be 0, this will be 0 because they are on the y equal to 0 line, and this will be 4 meter times m3. Okay, and then m1 m2 plus m3, something like this. So if you have some combination something like this simulation, then we have to determine both the x coordinate of the center of mass and y coordinate of the center of mass. Okay, all right, so with this I'm going to stop here, and then in next class, in next lecture, we are going to basically solve some of the related problem. Okay, the related problem means we are going to use the momentum, impulse, conservation of momentum, elastic collision, inelastic collision, perfectly inelastic collision, and the center of mass. Okay, so using this concept, we are going to solve some of the problem in next lecture. Okay, so that's it for today.